So, we are surrounded by AI models, right? They're predicting everything from the weather to what we're going to buy next. But here's the big question. How do we actually know we can trust them? When an AI gives you an answer, how can you be sure it's not just guessing?
Okay, imagine this. You've just built a predictive model and it's telling you it has 99% accuracy. Wow, that sounds amazing, a home run. But what if I told you that incredible score might actually be a giant red flag? Yeah, believe it or not, sometimes a score that good is a sign that something is very, very wrong.
The reason for that deceptively high score often comes down to one of the most classic problems in machine learning. It's called overfitting, and it's exactly how a model can look like an absolute genius on paper, but then completely fall apart in the real world. Think of it like this. You've got a student who's cramming for a big exam. Instead of actually learning the concepts, they just memorize the exact answers to the practice test. Sure, they'll get a perfect score on that practice test, no doubt. But the second they see the real exam with new questions, they're toast. An overfit model is that student. It didn't learn, it just memorized. So what you end up with is a model that's an expert on one specific set of data, but it's a terrible generalist. This gives you what we call an optimistic bias. It makes you think you have this brilliant all-knowing model, when what you really have is a one-trick pony that's totally useless the moment you show it something new. So how do we get around this? How do we get a truly honest look at our model's abilities? Well, that's where a really powerful technique comes in. It's called cross-validation, and it's all about building real trust in what our models can do. At its heart, cross-validation is just a much smarter way to test your model. Forget one big final exam. This is more like a series of tough pop quizzes spread out over time. It's specifically designed to see how the model handles data it's never ever seen before. And that's the ultimate test of whether it actually learned or just memorized. And the real key here is that we're not just testing it one time. We are systematically testing the model on different little slices of the data again and again and again. By averaging out all those little quiz scores, we get a much more stable, much more realistic picture of how it's actually going to perform out in the wild. Now, the most popular and, frankly, the most intuitive type of cross-validation is something called K-fold. It sounds a little technical, I know, but the idea behind it is actually super straightforward. So, here's how it works. You take your whole dataset and you just chop it into a few equal-sized pieces. We call these pieces folds. Then you just pick one of those folds and you set it aside. That's going to be your test data. All the other folds, that's what you'll use to train the model. The process is really clever. Let's say we split our data into 5 folds. In round 1, we train the model on folds 1 through 4, and we test it on fold 5. We write down the score. Then, for round 2, we train it on folds 1, 2, 3, and 5, and we test it on fold 4. We keep doing this, swapping out the test fold each time until every single fold has had its turn being the final exam. Then we just average all those scores together to get one single, really robust result. Now, you can choose any number for K, but just a little insider tip for you. In practice, you'll see tenfold cross-validation used all the time. It just tends to be a great sweet spot, a really good balance between being thorough enough to trust the results and not taking forever to run. But K-fold isn't the only game in town. It's important to know that cross-validation is really a whole family of techniques. It's not a one-size-fits-all tool, and different methods have different strengths. So, for instance, you have K-fold on one side, testing on these chunks of data. But on the other extreme, you have a method called leave one out. And it does exactly what it sounds like. It takes just one single data point, uses that for the test, and trains on everything else. And then it repeats that for every single point in your entire dataset. It's intense. So why would you pick one over the other? Well, it all comes down to a trade-off. K-fold is way faster and usually gives you a really stable, reliable performance estimate. Leave one out is unbelievably thorough, but it can be incredibly slow and computationally expensive. Plus, its final score can sometimes be a bit unstable. That's why, for most situations, K-fold is the go-to choice. It's just the perfect balance. All right, this next part is maybe the most important thing to remember. Cross-validation is an amazing tool, but it is surprisingly easy to mess up. And if you make one of these common mistakes, you can completely invalidate your results and end up with a false sense of confidence in a bad model. This quote right here gets to the absolute biggest mistake people make. Any step in your process that involves learning from the data, like picking which variables are most important, That step has to happen inside the cross-validation loop. For each and every round, you have to pretend that that round's test data is in a sealed vault and doesn't even exist yet. This mistake has a name. It's called data leakage. If you, say, analyze your entire dataset to pick the best features before you even start cross-validation, well, your model has already peeked at the test data. It's seen the answers. That gives it an unfair advantage, and information from the test sets leaks into the training process. The score you get at the end will be misleadingly high and totally useless. And one last really crucial warning. This whole method is built on a simple assumption that all your data is representative of the same thing. If you train your model on data from, say, customers in California, but then you test it on customers from New York, your cross-validation score isn't going to tell you anything meaningful about how it'll perform in the real world. So let's just quickly recap the 3 biggest takeaways here. 1, always be skeptical of a single amazing score on your training data. It could just be overfitting. 2, use cross-validation to get a much more reliable, much more trustworthy estimate of how your model will actually do. And 3, the absolute golden rule, to keep your results honest, every single step of your modeling process has to happen inside those cross-validation loops. No peeking. So what we've seen is that a single headline number like 99% accuracy can be really, really misleading. But now you know the secret. You understand the power of proper validation. So the next time you hear about some amazing new AI with stunning performance, your first question shouldn't be, wow, it should be, okay, but how did you test it?